And I'm happy to invite now Ziv Freund, the head of AI at Elbit Systems, ISTAR and EW, Elisra, that will talk about the known unknowns, deep clustering, and novel class discovery of wireless spectrum activity.
The known is finite, the unknown is infinite. This is a very nice saying, and it is attributed to Thomas Huxley, who was a biologist in the 19th century. He worked with Charles Darwin. And as I understand what he meant was that, although we've made so many amazing achievements, still so little do we know when we look, at all the things that we never understand. But, if we take it to the context of machine learning, then the finite, the known, is our training set, right? And the unknown is what will happen when we'll go to the field and test our model. And the question is, well, are there any known unknowns, things that we can expect that are different from our training set and what will actually happen when we go out to the field, and we actually can prepare for them. So let's look at an example of one use case that we at Elbit Systems are very interested in, and it is real-world spectrum activity classification. This is also working? Yeah, okay. I'll go back to... So what is spectrum activity classification? So the idea is that, there are many transmitters out there, right? If you open a receiver and you just look at all the transmissions in the spectrum, almost everything today is transmitting: your car, your phone, your refrigerator, any drones, so many things. And our goal is to just know everything that is happening in the spectrum. So the first step is to detect. So you can see here on the right, for example, a spectrogram. The x-axis is the frequency, the y is the time. And all these bounding boxes are transmissions. Some transmitter decided to send some information to another receiver at a specific time and frequency. So that's nice, but it's not enough to detect. Our goal is also to classify. And by classifying, I mean that we need to be able to say exactly what is the transmitter. What is the device that is transmitting? Who is the manufacturer of this device? And I think, you can understand for yourself that it's just impossible to have all the devices in the world exist in your training set. So we're able to record some devices, but, even if we're really good, so, next week, probably 10 more transmitters are going to come out by new manufacturers. So it's just impossible. But still, we are required by, our customers to be able to classify each transmitter, even if we haven't seen it before, even if it doesn't exist in the training set. So how do we approach such a problem? So if we go to the literature, there are basically two options. One is called open set recognition. And this is, maybe simpler. In this example, we have 4 known classes that exist in the training set. And when we go out, we see samples from the known classes, but also from new classes. So obviously, we want to classify the known samples to the known classes. And open set recognition requires us to classify the unknown, the new samples, just say they are unknown, just say they are new. But don't classify them to one of the known classes. This is like the big no-no in this case, because we don't want to say, okay, this is a transmitter from, this is a drone from this provider, although this is something else, just because we assigned it to one of our classes. So this is what we don't want to happen. So this is relatively easy, because if we know our classes, we can just learn the distribution and apply anomaly detection. But what I want to speak with you about today is the more challenging topic of actually finding out these novel labels, novel classes. So this is what I want to perform at the end. So I want to be able to classify the samples to the known classes, but I also want to understand that there are two new labels, 2 new classes in the data set. I want to assign labels to them, and I want to classify the samples to these labels, to classify these new samples to the new labels. So this is the task that we want to perform. And the question is how? How are we going to do this? So this is a relatively new field of research in the literature. But if you think about it, maybe it's not so complicated. Maybe it's just clustering. For example, I can do this. I can take my labeled data set, use it to learn representations. Then I go out to the field, I get my unlabeled data set, and I have good representations. I just run clustering, run dbScan, write k-means, whatever you want, spectral clustering, and then I already have the clusters. Now all I need to do is just say which cluster is known, which is unknown. I can do that by matching between the clusters to the known clusters, and then I can get the required results. Problem solved. The only problem is that when you actually try it, it's not working. You get really poor results. And there are two reasons to this. One is that it's difficult to learn representation, just a good representation just on the known classes, and then go out to the field and see so many new things. The representation is just not good enough, and the clustering algorithms are not so robust. Okay, if your classes don't look very nice, they really lie. I mean, they can just fail, very significantly. So what can we do? What can we do better? So the first thing that we can do better is look at the representation learning, because if we know we are going to perform clustering later, maybe we should invest in the way we learn our representations. So here you can see samples that I took from the open dataset Radio ML, which has 24 modulations. Each sample is actually a communication signal, so it means that it's complex. So I trained a convolution network, a 1D convolution network with 2 input channels to learn the representation. And in the beginning, I just started with just a simple classification loss, just a cross-entropy loss. So this is the embedding that we were able to learn. And you can see that we have some problem. For example, one class is split into 2 clusters. And this is very typical to communication signals, because transmitters usually have discrete modes. And once we try to learn the representation, then the representation by the network obviously may split them to 2 different clusters. And this is something, of course, that we want to avoid, because we may split these cases into two new classes. So how can we solve this? We can add regularization. For example, if our clustering algorithm is k-means, so k-means like our samples to be close to the center, dense, around the center. So we can ask our representation learning to do that exact same thing. We can use batch statistics. If we have a certain batch, we can look at all the samples that we have in this batch, or go to the first class. We know, since it's supervised, we have the labels, we know which samples are coming, for example, from the first class, calculate the center of the class, the current center, with the current representation, and just measure the distance between all the samples from that class to the center, and add it as a regularization, and just use this as a regulator. And indeed, this solved the problem. You can see that now all the clusters are converged together. So this is one thing that I should think about, but I want to do better, because right now I'm training my representation and then I'm doing clustering, but this is not what I want to do. We all know that the best thing to do is to train end-to-end. I want to train after the clustering. Can I do that? So the problem is that most clustering algorithms, actually every clustering algorithm that I know is not differentiable. Also, they're very compute intense, so it's not practical to do backpropagation through the clustering algorithm. I cannot do this. So, but still, I really want to learn end-to-end, so what can I do? So this is the solution that I'm going to show you, and this is actually where novel class discovery also comes to help, the setting. So let's see how we can do that. So we have our representation network, and now we need to perform clustering. But if we think about it, a deep network is actually, a classification network is actually can be used as a clustering algorithm, because the sample comes in and we just give probability according to which cluster do you think that is, it matches the most. So if we train this network, then we have a clustering algorithm. So we replaced the classical clustering algorithm off the shelf with a process of training a deep neural network. So of course, we need to, for each cluster, every time you want to write dbScan, instead you need to train a deep neural network. So there is a cost. But maybe now I can do this backpropagation through the clustering algorithm. So this is nice, but I still need a loss, right? Because of course I need to train this network on all my data, my unlabeled data as well, which before I just trained it on the labeled data, so there was no problem. But now, of course, I need, the clustering network has to see also my unlabeled data, which is not supervised, so not labeled. So how can I do? So the idea that is working quite nicely is to use contrastive learning. The idea is that I take two samples and I use my supervised data just to measure what is the chance that these two samples come from the same class. That's it. So this pseudo-labeling or this similarity measure, it doesn't have to be very accurate, it's soft, and I can use it so once I see two samples that I think, or actually I'm even certain that they come from the same class, I can use KL divergence in order to say that their distributions also should be the same. Okay? And if I'm certain that they are coming from different classes, then I want, of course, the distribution to be very different. So I can use contrastive KL as my loss function, and that's it. That's the idea. And now on this I can train. I can also add the clustering regularization that we saw before, and I can also stabilize the learning even more by using my labeled samples as well as part of the training, just by plugging them in, since I know to which, what is the expected result of the clustering network for each of the labeled samples. So I don't need the contrastive KL for these examples, just a regular classification loss. So that's the idea. These are the results from the paper, and you can see that the first row is just using k-means on the representations that are learned on the supervised data. The second row is using also the unlabeled data with self-supervision. Of course, this is much better, but in our domain, as Itai said earlier, we don't know how to do self-supervision for signals yet, good self-supervision. Maybe next year we will speak about it. But you see that improve the results, and you can see what happens when you use the method that I've shown you just in the previous slide. I also wanted to show our results, but sadly we didn't get the clearance on time, so I cannot show them. So this is something that hopefully I will show, this is a depth that I have to close. So that's it. I'll skip about how to set the number of clusters. This is also something because we don't know the number of clusters, but I don't have time. So just to sum up, we always need to think about what is going to happen when I'm going to take my system to the field, and all these unknown labels. Do we need to do something about them? Evaluation is something that is very difficult in this case because the results really depend on which. If I have data, of course, I need to, use a validation set, and the validation set, which are the classes that I learn, the known classes, and which are the classes, that I consider as new classes, that really affects the performance. And of course, it's understandable, which are the known classes. So I have to do cross-validation on this, and this takes a lot of time. And last thing is that, recent papers in this field are using foundation models. They come from vision, and again, we don't have a good foundation model for signals, so this is, again, bringing us to the self-supervision. If you want to hear more about this, there is a podcast, the Explainable podcast. There's a talk that I gave there about 2 years ago. So it's in Hebrew, and it's less rushed, so you can take your time and listen to it if you're interested. And that's it. Thank you.
Thank you so much, Ziv, for this amazing talk. Any questions from the crowd? We'll have maybe time only for one, so Amit over here.
Hi. I know you said that you only like end-to-end systems, but did you compare the performance to contrastive loss, but on the feature representation and then clustering? Like you cut the end-to-end like after the contrastive loss of the feature representation, and then just perform some sort of clustering algorithm. Would that work? And one more question. I know you didn't want to talk about it, but if your setting was to begin with, like you wanted to add new classes, how does that solve it if you fixate the number of clusters from the start? Like,
Yeah. So I'm sorry I didn't get the first question, but regarding the second one, so this goes to the number of classes. Of course, I don't know the number of classes in the unknown. When I go out to the field, I don't know how many classes I will see that are new. So, of course, I need to do something about this, but what we usually do is just, set a really, high number of clusters. And then I get more, of course, I get the number of clusters I determine, and then I do some post-processing by going on these clusters and just combining clusters that are too small and can be combined. And that's pretty much works well. Okay.
Great. So let's thank Ziv again for this talk.